The BB++ programming language. The history of memory management is defined by Collins in 1960 with reference counting, McCarty in the same year with the mark and sweep garbage collector, followed by Minsky, Still, Dijkstra, Baker, Hayes, Tofte. And as far as garbage collection is concerned, it's being used by the following programming languages such as ML, Haskell, APL Lisp, Ruby, Java, .NET, Smalltalk, ECMMA script, and a lot more languages uses the garbage collections. The advantage of the garbage collector is that it fixes dangling pointer bugs, it fixes double free bugs, it also fixes certain kind of memory leaks leading over time to memory exhaustion, and it's possible to override system allocators without modifying any code. Here's an example of the mark and sweep garbage collector. So we have here two containers. In the light blue rectangle represents the stack, a pointer on the stack, and the dark blue represents the heap. The pink and the red rectangles represents the node of a container. So if we have a pointer from the stack pointing to nodes to a list on the heap, then we'll have the following. And the mark and sweep algorithm is smart enough to destroy unreferenced nodes, such as the following. If we change the pointer of a node to a different one, then the job of the mark and sweep is to destroy the unreferenced nodes that we see here. Here's a second example of the mark and sweep, where the child node is directly referenced. And if we delete the pointer that points to the parent node, then the garbage collector is going to be smart enough to keep the following heap objects. The disadvantages of the garbage collector is that it cannot reclaim memory or invoke finalizers to make the destruction be done instantly. It cannot reclaim all unreachable objects, and it doesn't know which registers will be referenced. Here comes reference counting that is used mostly by C++, Rust, and Swift. The advantages of the reference counting is that the destruction is deterministic, it's predictable, and intrusive pointer binds counter and objects, thus it's fast. Here's a simple example of the reference counting. Once again, we have pointers in the light blue square that points to nodes of a container on the heap. So here we have two pointers pointing to the same node. And if we remove the reference of the first pointer to the first node, then the nodes are still going to be alive on the heap because the counter is still not null. Now here we see a problem with the reference counting. Here we see a container that is cyclic. The last node points to the first node. And if we delete the pointer from the stack to the first node, then the nodes are not going to be deleted because there's still going to be the pointer from the last node pointing to the first node of the container. So the disadvantages of the reference counting is that it can't handle cyclic references unless explicit weak pointers are used. And weak pointers fits best for hierarchical containers, but not for random structures such as neural networks or complex web pages. Now here comes root pointer. It has the following advantages. It has only one single machine instructions to get to the object. Only one memory allocations for the pointy object is necessary. The memory usage being a factor of 2. No need for special classes for array allocations and deallocations. All local allocations are guaranteed to be deallocated instantly upon exiting a scope. And it has all the benefits of an intrusive pointer. Here's an overview of the usage of root pointer in the C++ application. At each scope, we need to add a node proxy, and this node proxy will link all allocations made within that scope. So here we see the node proxy called X, and all the node pointers are being associated with that node proxy. Also here we see that we don't need special classes for array objects, etc. And here's the output of the example we just presented. We can see clearly that the cyclic references of class A is being neatly deleted. Now here's how root pointer works. Once again, if the light blue rectangle represents the stack, the number 1 being the node proxy and a pointer, the same with number 2 being a node proxy and a pointer, but each of the numbers being in a different scope. And then we'll have the following. Now if we exit scope 2, then the pointer and the node proxy associated to scope 2 are going to be both deleted. Therefore, the whole container is linked to pointer 2 will be deleted as well. Here pointer 2 is referencing a cyclic node. Now if we exit scope 2, then the pointer is going to be deleted, but the smart pointer is not enough to tell the container to be it's time to be destroyed. Therefore, the node proxy, when it's being destroyed, is going to be able to tell that now's the time for the container associated to number 2 to be destroyed. In this example, we see a child node being directly referenced from a higher scope. And if we exit scope 2, then the container which was promoted is still going to remain alive within scope 1. The root pointer disadvantages are only the following: that it cannot be easily interchanged with shared pointer or a raw pointer. Now here comes the BB++ language that is really a wrapper over the C++ language, but adds the following powerful features, such as it adds instances of a node proxy implicitly at each scope. It adds implicit references to these objects in top-level classes. It overloads operator dot, uses the keyword auto for member variables instead of the keyword decal type. It adds metadata of the classes in order to propagate the proxy associated to the pointer within those classes. For example, if we have the following function that contains an object with a cyclic reference within it, it has to be mentioned also that the node proxy is being instantiated at each scope. Then we'll have the following output. We'll see that the cycle is being destroyed before we exit the function. Now here's a second example where we have the exact same thing, except we return the cycle itself to the parent scope. Once again, at each scope we have an implicit node proxy. It has to be mentioned also that the node proxy contains the following characteristic, which is the depth level of each scope. So the function main contains a node proxy with the depth level 1. Within that main function, there's going to be the bar function that has a depth level of 2. And if we exit that bar function, we're going to compare the depth level of the object being returned with the depth level of the calling function. So we'll see here that the depth level are going to be different when we return from that function. What happens here is that the proxy used by the parent scope is going to be propagated to all the elements associated to the document instance. So therefore the entire cycle and all the child elements of that cycle are going to be promoted to the parent scope. Once again, as we explained before, the container is being promoted in that case to a higher scope. Therefore, the document elements are all going to be destroyed after the number 2 is going to be printed out. Now here's the same example, but which has a member function within that class. In this new example, we simply call the foo function, which is a member variable of the document class, returned by the function bar. Then we'll have the following output. We see that the foo call is named lambda 0 in this example, and this this cout is being done before printing the number 2. And after printing the number 2, we print the destruction of all the instances of the document class. Now we see in this example, the example of a JavaScript type of closures. These closures are simply illegal in BB++, and we can't reference a variable that informally exists. But we can convert this closures with a C++ type of reference, which then this reference can then be modified as much as we want by the function itself. So if we have the same example as we used before, then by calling the foo function once, is going to increment the temporary variable once, and therefore we should have the number 2 being printed out. And this is exactly what we have. We have the lambda being printed out, followed by the number 2, which is the temporary variable being incremented once, followed by another number 2 that is our constant being printed out, followed by the call to the document destructor being called 3 times. Now, thank you for your time, and here are the hyperlinks of the BB++ language and the root pointer itself, where we can find benchmark comparing the root pointer with the boost shared pointer, and we can see that the root pointer is a little bit faster than shared pointer in multi-threading mode. But more optimizations are to come. Thank you.